Section. Introduction. We're going to talk about a challenge that large language models, LLMs, face, and a solution we've come up with. LLMs are great at many tasks, like retrieval augmented generation and in-context learning, but they need to process a lot of information to do so. The problem is, these models are often limited by a fixed amount of context they can handle at once. For example, LLM A1 can handle 2048 units of context, and Llama 2 can handle 4096. This isn't always enough for real-world situations. We could train these models to handle more context, but that would take a lot of time and computational resources. Plus, if we focus too much on long sequence data, the models might not perform as well on shorter contexts. So, we need a solution that can extend the context length without compromising the model's existing abilities. Our solution is called Activation Beacon. The idea is that LLMs have a lot of redundant information in their raw activations, so we can condense this information into a more compact form without losing much. This way, the model can understand a lot of context even if it's only looking at a small window of it. This idea is similar to sparse attention and context compression, but our method has some advantages, like better context extension, efficiency, and compatibility with existing LLMs. In our method, we use special tokens called beacons to condense the raw activations. We place these beacons at different points in the context and use them to generate condensed activations for each specific interval. For an interval of length L, we use K beacons, where L is much greater than K, which gives us a condensing ratio of alpha equals L divided by K. These beacons are efficient and can be added to an existing LLM without affecting its current abilities. We process the condensed activations from the beacons in sliding windows. Each window contains some beacons and some ordinary tokens. The size of the window is limited by the maximum context length of the LLM, like 4096 for LLM A2. This way, we can process long sequence data one window at a time, which is much more efficient. We train the activation beacon by maximizing the likelihood of generating an ordinary token based on the beacons and the preceding ordinary tokens. We also randomly sample alpha during the streaming process, which helps the model handle different context lengths. We applied Activation Beacon to the Llama 2-7B model and trained it on a mix of data from Red Pajama and Long Alpaca. It only took 10,000 steps, or less than 9 hours on an 8XA800 GPU machine, to get good results. The model performed well on extended context lengths, like 8K, 16K, and 32K, and was competitive on tasks like question answering and few-shot learning. It could even handle context lengths up to 100K and 400K. In conclusion, Activation Beacon is an effective, efficient, and compatible way to extend the context length of LLMs. It doesn't interfere with other methods, like fine-tuning and retrieval-based methods, and can even complement them for even longer context extensions. Section Summary. The paper introduces Activation Beacon, a method to extend the context length of large language models, LLMs, without compromising their existing capabilities. By condensing the LLM's raw activations into compact forms using special tokens called beacons, Activation Beacon allows the LLM to perceive information from a vast context even with a short context window. This method improves the quality of long context generation, supports diverse context lengths, and enhances inference and training efficiency. Section. Activation Beacon. In this paper, we discuss a concept called Activation Beacon. To start with, let's talk about language model, LLM. It generates content by predicting the next word based on the words that came before it. This prediction can be represented as the probability of the next word given the previous words and the parameters of the LLM. However, current LLMs are limited by the maximum length of context they can consider, which hinders their ability to use information from long sequences of data. We propose a solution to this problem, condensing the raw activations of the LLM into a more compact form. This way, the LLM can process more information even if the maximum length of the context window remains the same. When the LLM predicts the next word, it looks at the activations within the context window for useful information. These raw activations are memory-intensive and expensive to process, limiting the size of the context window. To address this, we introduce special tokens, called beacons, that condense the LLM's raw activations into a more compact form. This allows the context window to take in more information from the previous context, improving the prediction of new words. We divide the entire context into intervals of a certain length and place a certain number of beacons at the end of each interval. In each decoding layer of the LLM, the input hidden states of the beacons are transformed to query the raw activations within the interval, producing condensed activations. We also explore 3 attention schemes for the beacons: segmentation, stepwise expansion, and full coverage. All 3 options have the same computation cost, but we found that stepwise expansion leads to the best performance. The condensed activations from the beacons, along with the raw activations from the regular tokens, are processed with sliding windows. Each sliding window consists of a certain number of beacons from the past context intervals, and the regular tokens from the latest context interval. The next word can be predicted based on the relative positions of the beacons and tokens within the sliding window, regardless of their absolute positions in the entire context. This method is efficient in terms of memory and time during training and inference, and it can cover a large number of past tokens on top of the sliding window. We introduce the beacon as a plugin module for the LLM. It is learned while the LLM's parameters are fixed, and it is only used to condense the raw activations for the past contexts. This allows the LLM to process long contextual information without affecting its existing capabilities on processing short context. The beacon is trained by auto-regression, where the next word is predicted based on the condensed activations from the beacons and the raw activations from the regular tokens. During training, we perform stepwise sampling at each interval where the condensing ratio is randomly chosen from a large range. This operation diversifies the condensing ratios and the number of beacons where the auto-regression is conditioned. Section Summary. The paper introduces the concept of an activation beacon, which condenses the raw activations of a language model, LLM, into more compact forms. By using special tokens called beacons, the LLM can intake more information from the previous context, allowing it to overcome the constraint of maximum context length and improve prediction of new tokens. The beacons are trained through auto-regression, where the next token is predicted based on the condensed activations from the beacons and the raw activations from ordinary tokens. Section. Experiment. We conducted several experiments to investigate various aspects of the activation beacon. These include its impact on long context generation capabilities, long context utilization capability, efficiency in terms of GPU memory and inference time, and the individual contribution of different technical factors. We applied our method to the Llama 2-7B chat model for empirical studies, using a mix of 80,000 samples from red pajama and long alpaca. Each sample sequence length ranged from 1024 to 8192, with an average length of 3180. We used a single machine with 8A800 GPS for training, which was carried out for 10,000 steps with a batch size of 8 and a learning rate of 0.00005. The length of each context interval was set to 1024, and the condensing ratio varied between 2 and 128 during training. Llama's parameters remained constant throughout the training process. We compared our method with several baselines, all based on the Llama 2-7B chat model. These included the basic method, fine-tuning free methods, fine-tuned full attention methods, and fine-tuned methods with adapted architectures for long context. We used FLASHATTENTION2 to speed up self-attention computation and save GPU usage for all the baselines. However, due to its use of a customized attention scheme, Activation Beacon is currently incompatible with FLASHATTENTION2, so we used the scaled dot product attention from PyTorch for acceleration. We tested long context language modeling with 3 datasets, PG19, ProofPile, and CodeParrot. For PG19, we used its entire test set of 100 books. For ProofPile, we extracted archive papers from the test set and sampled 100 texts for evaluation. For CodeParrot, we formed long sequences by concatenating code from the same repository and sampled 100 sequences for evaluation. We computed the perplexity with a sliding window of size 2048. Our results showed that Activation Beacon significantly improved long context language modeling performance. It outperformed the Llama 2-7B baseline and the fine-tuning free methods, and its performance was comparable to or even better than the fine-tuned full attention methods. Importantly, Activation Beacon was able to extend the context length to 100K, where most of the baselines became either ineffective or ran out of memory. In fact, Activation Beacon remained effective even when the context length was extended to 400K, which is 100 times the maximum context length of Llama 2 to 7B. Furthermore, unlike many alternative methods, Activation Beacon does not require any long sequence training data to acquire such a super long context capability. Section Summary. The experiments in this section aim to explore the impact of Activation Beacon on various aspects, including long context generation capabilities, long context utilization capability, efficiency in terms of GPU memory and inference time, and the individual contribution of different technical factors. The method is applied to Llama 2 to 7B for empirical studies, trained with a mixture of data from Red Pajama and Long Alpaca, and achieves superior long context language modeling performance compared to baselines and fine-tuning free methods. Activation Beacon also enables a much longer extension of the context length, up to 400K, without requiring long sequence training data. Section. More long context tasks. We've further explored 5 practical tasks from Long Bench, which include single document question answering, multi-document question answering, summarization, few-shot learning, and code completion. The results of these experiments are presented in a table. We also assessed a topic retrieval task, with the results displayed in a figure. Our Activation Beacon model showed significant improvement over the Llama 2 to 7B model and other models that don't require fine-tuning. It also performed comparably to models that do require fine-tuning. This is impressive, considering that many of the evaluation samples could be almost entirely covered by a context window of 16,000 or 32,000 words, setting a high standard for this benchmark. We were curious about the source of the fine-tuned model's empirical advantage, given that fine-tuning alters the original parameters of the language learning model, LLM. To investigate, we compared the performance of LONGCHAT32K and LONGALPACA16K at a context length of 4,000 words, where they use the same information as the Llama 2 to 7B baseline. Interestingly, both models significantly outperformed Llama 2 to 7B on every task. In terms of efficiency, we evaluated the running efficiency at inference time in terms of time cost and GPU memory usage. Activation Beacon had a much smaller GPU memory usage at long context lengths compared to Long Chat and Long Llama. Activation Beacon and Streaming LLM had similar memory costs as both methods are based on sliding windows. In terms of inference time, Activation Beacon was faster than Long Llama but slower than Long Chat when the context length was short. However, as the context length increased, Activation Beacon caught up and eventually surpassed the full attention methods in speed. We also compared our training cost with Long Alpaca, which is known for its high training efficiency. Under similar hardware conditions, the training of Activation Beacon could be completed in just 9 hours, which is even faster than the reported time cost of LONGALPACA16K with S-squared attention. In our ablation studies, we evaluated the impact of different technical factors, including the attention scheme of beacons, the sampling strategy of condensing ratio, and the composition of training data. We found that the attention scheme had a significant impact on Activation Beacon's performance on both long context language modeling and long context understanding. The stepwise expansion works with the gradually expanded attention scope, enabling the beacons to acquire different levels of local and global visibility of each context interval, which notably improves the performance. The sampling of condensing ratio is another influential factor. We compared 2 alternative strategies, the instance-wise option, which samples 1 condensing ratio for all context intervals of each training instance, and the monotonous option, which uses a constant condensing ratio of 4. The stepwise sampling strategy, which introduces the most diversified condensing ratios for auto-regression, resulted in the strongest performance for every evaluated context length. Lastly, we observed that using only Red Pajama as the training data already led to a competitive performance on both evaluation tasks. The introduction of more training data from Long Alpaca contributed little to the language modeling task, but it substantially improved the long context understanding performance on single doc QA. Section Summary. In this section, the authors evaluate the performance of Activation Beacon on various real-world tasks and compare it with other baselines. They find that Activation Beacon performs comparably to fine-tuned full attention methods and shows a notable improvement over Llama 2 to 7B on different tasks. The authors also analyze the efficiency of activation beacon in terms of time cost, GPU memory usage, and training cost, and find that it has a smaller memory usage compared to other methods and its time cost is linear to the context length. Additionally, the authors conduct ablation studies to evaluate the impact of different technical factors on activation beacon's performance and find that the attention scheme, sampling strategy, and training data composition all play significant roles in improving its empirical performance. Section: Related works. Let's delve into the various research efforts that have been made to extend the context length of language learning models, LLMs. A number of strategies have been developed to expand the context window of LLMs. For instance, Alibi uses a technique called linear decaying attention biases to extend position encoding. Other methods, such as position interpolation, NTK-aware scaling, and rerope, build upon rope to enable LLMs to handle unseen positions during inference. While these techniques can be applied directly to a well-trained LLM, it's often beneficial to fine-tune the model so that the extended context can be used more effectively. However, fine-tuning with long-sequence data can be costly. As a result, several new methods have been developed to reduce training costs. For example, Long LoRa uses a technique called S-squared ATTN and leverages LoRa for cost-effective training. Pose, on the other hand, uses skipwise position indices to train LLMs on a 2K context length, simulating a 128K context length. Despite these advancements, fine-tuning can still be prohibitively expensive when dealing with extremely long contexts. Furthermore, the fine-tuned LLM still relies on full attention, which can be costly during inference, even with acceleration techniques like flash attention. Additionally, fine-tuning may negatively impact the LLM's performance on short contexts. In contrast, our method can be easily integrated with existing LLMs and offers greater efficiency during both training and inference. The quadratic complexity of self-attention is a significant obstacle to achieving long contexts with transformers. Previous research has attempted to overcome this issue by using sparse attention or approximate attention computation. However, these methods face challenges such as the need for customized GPU kernels for specific matrix-matrix multiplication variants, reliance on global attention patterns unsuitable for autoregressive language models, and incompatibility with well-pre-trained models. Our method, however, is free from these constraints and can be easily incorporated to extend the context of LLMs. Another approach is to offload the long context to external memory devices and retrieve useful parts as needed. This retrieved data can be either chunked input or cached key-value activations, as seen in memorizing transformers and long mem. This concept has been further developed in recent research. For example, landmark attention uses a special token to represent a chunk of activations, enabling more efficient computation of retrieval. Focused transformers propose contrastive training to improve the discrimination of relevant keys from cached data. These retrieval-based methods, similar to ours, aim to condense the context but approach the problem from a different angle. It's also possible to introduce long contexts on top of sliding windows. For instance, streaming LLM and LM Infinite can achieve an infinite context by only maintaining the activations for the first and latest tokens. However, they can't fully leverage the rich information within the long context as the portion beyond the sliding window is ignored. While some research has attempted to use summarized or compressed memory to address this issue, there is still a significant loss of long contextual information due to existing memorization mechanisms. In contrast, our method offers both high operational efficiency due to its streaming mechanism and effective utilization of the long context thanks to its high-quality condensing of activations.